Hello and welcome to The Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain. Today we're going to be joined by a special guest, Dr. Darby Dyer, who will be talking about new research on Venus. But before that, let's take a look at the news. While the American Astronomical Society meeting is over, we still had news stories coming out after we recorded our episode on Friday. And today we start with one of them. During a press conference, RIT's Joel Castor presented new research on the long-observed Jewel Bug Nebula. From a regular telescope on the ground, this remnant of a dying star looks like nothing more than a fuzzy bug-shaped blob. But even early Hubble images revealed an intricate structure of glowing gas and dust. And with each new camera upgrade, HST has revisited this system to see what new details could be resolved. The Jewel Bug Nebula is what's called a planetary nebula, a complex system of dust and gas that has been blown off of a dying star. Astronomers don't entirely understand how these complex shapes form, but we do know that we're dealing with the effects of a star exhaling its atmosphere in pulses, and that material is interacting with a companion star or planets that may be in the system. The Jewel Bug Nebula is estimated to be about 600 years old, or roughly the age of a vase from the Ming Dynasty. In this time, material has been moving out and away from where a 1 to 8 solar mass star once shined. And as that material moves away, it has been cooling. The core of the star, now a white dwarf, should still be in the center, giving off bright ultraviolet light. But astronomers haven't been able to find that star in this system yet. And what appears to be a star in the center is actually just a chance alignment of a random star between us and the nebula. By looking to see where different kinds of gas and dust are visible, it becomes possible to map out the temperatures of the gas. The violet appearing structures in the Hubble image, mapped in red in the not very pretty structural map on the right, is just dust, which occurs where temperatures are coolest. Some of the brightest gas is hot shocked material with ionized iron, and it appears blue. And the remaining material is a more moderate temperature that can be mapped out by looking for ionized sulfur. According to Kastner, we're able to see the effect of the dying central star and how it's shedding and shredding its ejected material. We're now seeing where material that the central star has tossed away is being dominated by ionized gas, where it's dominated by cooler gas, and even how the hot gas is being ionized, whether by the star's ultraviolet or by collisions caused by its present fast winds. One of the most amazing and frustrating things about planetary nebula is the variety of shapes they come in. In addition to viewing the Jewel Bug Nebula, Kastner and his team also observed the roughly 2,000-year-old Butterfly Nebula. Both the systems are thought to have binary stars in their core, and it is possible that the reason they look so remarkably different is simply viewing angle. In this system, the narrow body of the butterfly is the dust, and the hot ionized iron traces the top of the right wing and the bottom of the left. The object isn't actually flat, however. The butterfly is more like an hourglass viewed edge on, while the Jewel Bug Nebula is more like a really warped hourglass viewed from the top down. What was presented at the American Astronomical Society meeting is only the beginning of this research, and we look forward to seeing more nebulae analyzed and a longer research paper in the future. When those come out, we'll bring them to you here.
In what may be our final story from the AAS meeting, we'd like to share the discovery of one of the earliest forming massive galaxies in our universe. Cataloged with the phone number J0313-1806, this object was detected in part from the DESI survey, which we discussed last week. This object now holds the record for most distant galaxy ever seen, and its light has been traveling to reach us for more than 13 billion years. The only reason we can see this system is it is just truly massive in about every way. This system has a huge supermassive black hole that is 1.6 times 10 to the 9 solar masses, or 1,000 times larger than the supermassive black hole in our own Milky Way galaxy. The system is undergoing massive amounts of star formation and is creating 200 stars per year, compared to our own galaxy's roughly 1 star a year. It's an amazing system, and to be entirely honest, it is also totally unexpected. In order to get a system this big, either massive amounts of material had to collapse all at once to form that supermassive black hole and galaxy, or stellar mass black holes needed to form and then merge at a rate we didn't think was possible. According to lead study co-author Xiaohe Fan, we have to look much earlier in the universe and look for much less massive black holes to see how these things grow. This kind of research may require the JWST, so here is to hoping it can finally get off the ground later this year. This work will appear in the Astrophysical Journal Letters and was led by Feige Wang of the University of Arizona.
Before we go to break, we have some good news for all you particle physics junkies. It looks like the Axion might just be starting to reveal itself in unusual flashes associated with nearby neutron stars. A favorite of sci-fi authors and showrunners, these particles were theorized in the 1970s as one of the fundamental particles of our universe. If they exist, they have mass and just might be part of the hidden dark matter that makes up so much of our universe. They also have this neat predicted property of converting into light in the presence of strong magnetic fields. Well, some of the strongest known magnetic fields are associated with neutron stars. And there are 7 young, not too distant neutron stars in utterly boring regions of space that shouldn't have X-ray light, but have an excess of X-ray light that can't be explained by anything we know of other than axions or unknown physics. This X-ray light was seen in both the Chandra and XMM Newton X-ray telescopes. According to study co-author Raymond Coe, we're not claiming that we've made the discovery of the axions yet, but we're saying that the extra X-ray photons can be explained by axions. It's an exciting discovery of the excess in the X-ray photons, and it's an exciting possibility that's already consisted with our interpretation of axions. This work is published in the journal Physics Review Letters and is led by Malte Buschmann. No matter how it turns out, new physics or axions, this is exciting news, even if it does break the brain a little. After the break, we're going to bring things back down to Earth before visiting a few other worlds. With the start of each new year, we start hearing reports of how the 12 months we just completed stack up against all the cycles of the 12 months that came before. One of the more unfortunate metrics that has been in the news is our Earth's temperature. According to newly released NASA data, 2020 was tied with 2016 as the warmest year on record and was on average 1.8 degrees Fahrenheit or 1.02 degrees Celsius warmer than the baseline from 1951 to 1980. Now, there are a lot of ways for a world to be warmer on average, and some places, maybe your place, will see a change of more than just 1 degree. What we're observing in some places are several degrees warmer seasons, while other places are seeing things a couple of degrees below. But where those warmer and cooler places are located really matters. When it's the oceans that get heated, we see bigger hurricanes and more melting ice. It's hard to fathom how much energy the ocean can store. In 2020 alone, it is estimated the oceans absorbed enough heat to boil between 65 million and 1.3 billion kettles of water, depending on your science model and the size of your kettle. We saw that energy shaping our world with the accelerated melting of Greenland's glaciers and Antarctic ice, and the supercharging of tropical storms. Currently, a massive piece of the Antarctic Larsen ice shelf is grinding toward South Georgia Island, which is home to penguins, sea lions, and a multitude of critters that must have access to open water to find food. There is significant concern that as this melting iceberg tries to make landfall, it could block access to the ocean for these animals. It's hoped it will run aground far out to sea, and the animals will still have access to the free ocean. As exciting as it is to scientifically see a world so rapidly changing, this is all a lot to understand. And in fact, my dog is also saying it's a lot to try and understand. Apologies, we do record this show live. This is all a lot to understand as someone who's living on that planet that's so actively changing. If we don't want to see more radical changes, we, all humans on this planet, are going to need to do our best to reduce the release of greenhouse gases. Our individual choices matter, but the biggest impacts come from industrial pollution. And with the US expected to rejoin the Paris Climate Act on Wednesday, it is easier to hope that we can succeed in reducing the rate of the world's temperature rise.
Thank you for ending that story on a hopeful note, Pamela. From the woes of Earth, we head out to Jupiter to talk about the largest moon in our solar system, Ganymede. I've talked about Ganymede quite a bit recently, especially if you watched our Minecraft Monday show back in December. We added a few features onto Ganymede in our Minecraft solar system based on research of the past few years, including an atmosphere with aurora and a subsurface ocean. Yes, Ganymede is another icy world, and new research published in the Journal of Geophysical Research Planets uses data collected from NASA's Juno mission to evaluate some of that ice. The team involved used the Jovian Infrared Auroral Mapper, GIRAM, to take images and spectra of Ganymede. In particular, they looked up at the North Polar region. Juno was about 100,000 kilometers away, so GIRAM was able to map at an impressive resolution of 23 kilometers per pixel. From a collection of images taken at various angles, researchers compared the differing brightness levels and the illumination geometry and developed a model for the surface reflectance. They also extended the current map of global water ice to these polar regions. The biggest result from this paper is the discovery that there are likely larger ice grains in relatively fresh craters, a result that needs further explanation. Lucky for us, we told you last week that NASA extended the Juno mission, and Ganymede is going to be on the receiving end of more flybys that will be even closer. We're excited to see where this research leads.
Jupiter is definitely the big planet on campus here in our solar system, what with that huge moon and its own significant size. But in the wider galaxy, Jupiter is a small fish in a big pond, and it's not even the most interesting Jupiter-sized planet in that big pond. In a new paper appearing in the Astronomical Journal, a team led by Carolyn Paulette presents the discovery of a puffed-up planet, roughly the size of Jupiter. The world has 10 times less mass than Jupiter. It's basically just a lot of hot gas with a less than 4.6 Earth mass core. It is thought that it normally takes significantly more mass in the core for a planet to gravitationally pull in enough material to become this big. This object has been cataloged as WASP 107b and has been dubbed a superpuff or a cotton candy planet. Co-author Bjorn Bentke states, "This work addresses the very foundations of how giant planets can form and grow. It provides concrete proof that massive accretion of a gas envelope can be triggered for cores that are much less massive than previously thought. It's unclear if the team has considered any other ways of getting a puffed out planet than forming it that way. This is, after all, a discovery paper saying, hey, look at what we found. I have to admit, this work reminds me of a paper last year that pointed out that Jupiter's core is fluffier than expected, probably because of a collision between Jupiter and an earlier protoplanet. That paper has me wondering if you can get really fluffy planets with bigger collisions. I can't wait to see what theorists do with this discovery. After this break, we will be back with a less fluffy and more acidic planet as we take a look at Venus and bring on Dr. Darby Dyer to discuss her latest discoveries.
Welcome back. Last week, our home institution of the Planetary Science Institute sent out a press release about a trio of papers about Venus, including one that was published in Science Advances on Friday. The other two papers were published in the journal Icarus and in Geophysical Research Letters. PSI's Darby Dyer is lead author on those last two and a co-author on the Science Advances paper. Here are the basics. Venus is covered in very thick clouds of carbon dioxide. This cloud layer makes it incredibly difficult to get any information about the surface of the planet, as most visible and near-infrared light cannot penetrate. So we cannot get spectra of the rocks on the surface. A few Soviet landers managed to acquire some data from back in the 1970s, and the Magellan mission obtained some radar data. It's not a completely hopeless situation, however. There are some tiny windows in the near infrared at about 1 micron that can penetrate the thick clouds. So let's send an orbiter. But wait, the question then becomes, how will we know if the data we acquire through those windows with that expensive orbiter is accurate when we've not sampled data in this fashion before? Laboratory work to the rescue. Dr. Dyer worked with a team out of the German Aerospace Center Institute of Planetary Research to set up a Venus chamber where they could work with rocks in a similar high temperature environment to that of Venus and acquire spectra. These spectra made it possible to understand what the composition of a variety of igneous rocks would look like as sampled by a Venus orbiter. The data was compared to spectra taken with those same Soviet landers and found to be a match. Now we can plan for missions like Veritas and ESA's Envision to include instruments that can perform the 6-wavelength spectroscopy tested in the lab. And we can even set up machine learning algorithms in advance to analyze the data from orbit, since we already have a data set to compare to. Very exciting prospects indeed. And now we're joined by Planetary Science Institute senior scientist, Dr. Darby Dyer. Dr. Dyer, thank you so much for joining us today. Did I summarize the work properly?
Thank you for having me. And yes, you did a brilliant job of summarizing it.
So to start with, can you tell us how the spectroscopic windows, I like the term windows, were discovered?
So I think it's long been known that in the laboratory, the spectrum of CO2 is opaque to visible light. And I think people didn't pay much attention to the fact that there were a few, if you want to think of it as cracks in the windows, that's what we saw. Just a few little areas around 1 micron wavelength where you can actually see through the clouds. And it wasn't originally thought that you could do much with such a tiny wavelength opening, but in fact, we've found that you can do a lot.
That's great. And so how does this help potential Venus missions like Veritas and Envision based on the work that you guys have done?
So it's confusing to people. You know, I'm a professor also, and it's confusing to show pictures of the surface of an object when they're radar images, because radar is not the same as visible light photography. And so I think that it will be a profound breakthrough if we can get an orbiter to Venus and actually start showing pictures of what this looks like under multiple wavelengths. We already have glimpses of this. The Venus Express mission, which was an ESA mission a few years ago. They had a sort of a proof of concept orbiter that looked at 1 wavelength at 1.02 microns, and they still produced some sort of dazzling maps, even though they weren't well calibrated and they were only in relative emissivity. they gave us really tantalizing glimpses of things like, maybe there are parts of Venus that are really, really young. And those data were used to suggest that maybe there are hot spots where there might be active volcanism going on the surface of Venus.
So we might be able to see like active volcanism and not just some of those pancake volcanoes that we've seen evidence of?
Absolutely. That's one of the things that excites me the most about the potential for this kind of spectroscopy, is we might be able to see active volcanism on the surface. We can also see some bands for water vapor. And of course, water vapor is often given out by volcanoes. So water vapor would also be an indication of an active volcano, which would be really cool.
Fabulous. So one of the things that I saw in the press release that I really liked was the mention that if we put these on these new orbiters, we can actually do machine learning. We can use machine learning algorithms in situ, basically. So how does that work? What does that look like?
So for the past decade or so, my research group has been collaborating with computer scientists, and I've been trying to teach myself, a geologist, how to do machine learning. And one of the things that I've learned about machine learning is that it's very good in situations that involve spectroscopy of features that are extremely subtle. And in this case, the 6 windows that we see through the Venus atmosphere are very, very close together. So they're really so close together that we can't look at peaks or bands in the way that we normally look at planetary data. But with machine learning, you can actually tease out really subtle differences that actually help you inform the problem that you're interested in, which in our case is what kind of rocks are present on the surface of Venus. We don't know whether the surface of Venus is completely covered with basalt or whether it's a combination of granitic, continental-like, Earth-like continents and basalts. We don't really know hardly anything about the
right. We have no idea if there are tectonics or anything. Okay, so we're going to take a quick break, and when we come back, we're going to talk to Dr. Dyer about what it was like trying to do science and produce papers in these unprecedented COVID-19 times. Stay tuned. Welcome back again. So Dr. Dyer, first off, I want to ask you, what was it like working on science in these very wild, unprecedented COVID-19, everyone's at home and not able to travel times?
It's been a challenge, but especially for me, I'm a laboratory scientist fundamentally. And in fact, one of the pieces of equipment that I use uses radiation. And because you can't turn radiation off, I actually had to go to the lab every single day, even during the lockdown. So I've actually seen probably even more of my lab than I normally do, because no one else was allowed on campus except me and a handful of other people.
Oh, so no.
That was a very strange feeling, to go into completely dark, empty buildings and just go do a sample change every day. But in other ways, yeah, it's been unprecedented. I'm part of the planning team for the Veritas mission. We're about to do our final presentation for NASA, and that's involved bringing together a team of more than 100 people, all remotely, many of whom I've never even met in person.
And you were working with the group in Germany as well, correct?
Right. So the German people, well, that's a funny story. So in order to get some data for these papers, some last minute data, we needed to get some samples from my laboratory in Massachusetts to Germany.
Oh no.
and this was in the end of March. This is literally when we figured out that we had to do these experiments. So we prepared this. I found somebody who could help me prepare the samples in his garage. So I drove to this guy's house, dropped the samples off. He cut them up in his garage. I went back and got them. And then we had to find some way of getting them to Germany because customs was backlogged.
And very few people can travel. And
correct. Right. So we ended up finding someone at the Planetary Science Institute who was going on June 1st, but we had to get her the samples. And to make a long story short, this was over Memorial Day weekend, and things were closed, and our samples, our very precious samples, ended up in the nail salon next to the Planetary Science Institute.
No!
Fortunately, the receptionist, Kimberly, was able to go retrieve them and then get them in the hands of this person who then hand flew them to Berlin, although she got stopped in customs because, of course, some of them were rock pouches and they looked kind of suspicious. So anyway, it all turned out well. We finally got the samples to Berlin.
So you had to get them from Massachusetts to Tucson and then to Berlin. Wow, that is some very extensively traveled rock samples there.
It was a miracle. When they finally got to Berlin, my collaborator and I had a Zoom where we drank champagne to celebrate.
And all your meetings, of course, are on Zoom. So how much of your time is spent on Zoom these days?
Oh, I think I've got probably 12 or 15 standing meetings a week. And I'm not teaching this semester. Normally when I'm teaching it would be many more, but because I'm not teaching it, it's only 12. But still, it's hard. You miss the casual brainstorming kinds of encounters that you have with people that are kind of the core of how you nucleate ideas in science. So that's been tough. But on the other hand, I think this is going to be a great model going forward, because it does make you feel in touch with your collaborators when you see their faces. All the people with whom I used to have phone conversations, now I get frustrated with the phone, and I say to them, let's just Zoom, I'm sending you a link. And I'll hang the phone up, and then I get to see their whole face. And that's
actually better.
Advantages. Yeah, so I think going forward, we're going to take some of these advantages and use them, and we're going to feel frustrated. I think the biggest problem is when you have a big group and you're trying to have a discussion. Very difficult to do with Zoom.
Yeah, that's true. That's true. You have to be careful about the crosstalk, and everybody's trying to get their voice heard. As far as the upcoming missions go, you said you're involved in Veritas. What is Veritas looking for other than the spectroscopic work that you're doing?
So Veritas has two important parts. One is an emissivity mapper that's going to make a geologic map of Venus, and the other one is something called a visar, which is going to do a radar map and give us both great topography and good radar signal from the whole surface. And the reason that's important, well, for a lot of things, if you have good topography data, then you can do things like look for trenches that might be indicative of nascent plate tectonics happening on Venus. So that's really neat. And it's kind of a shame. We haven't been to Venus in more than 25 years. And the topographic data that we have for Venus is worse than what we have for Pluto.
Absolutely. And this all became very important, of course, when over the summer it was the whole, there might be phosphine in Venus's atmosphere, and all of a sudden everybody's very excited about Venus. So that helps you out, though.
Oh yes, any interest. I'm also the chair of the Venus Advisory Group for NASA, and my slogan is any news about Venus is good news. So many questions. Recently, we've realized that maybe Venus had oceans for 3 billion years. And that just opens up all these different possibilities for life having been present there. Venus is also really typical of most of the exoplanets of which people are talking. So there's a lot of recent reasons why Venus has become even more important in planetary science. And I really hope that we get to go there.
Okay. One last question. Tell me about that fabulous scarf you are wearing. I think it looks a little familiar.
So this is the Magellan Venus map that was, this scarf was made by some former undergraduates of mine who digitized this and sent it off to get made for me. So I wear this scarf with pride.
That is fabulous. So wow, thank you for sharing. And once again, thank you, Dr. Dyer, for joining us today. We're really excited to have you here, and I'm really excited about the potential for this research.
Go Venus.
Go Venus.
Thanks, Beth.
Thank you. All right, this has been the Daily Space.